Hi, good evening. When we finished up class last night a little bit early, I told you that I was going to put a recording out there, and in fact, I'm going to put two recordings out there. I'm going to complete one, just kind of going over binomial distributions, and then I'm actually going to work through the homework that's assigned this week to answer some of the questions that came up in class last night, as well as some others that I think there's probably some questions about that we haven't covered thoroughly. So I'm going to do that as soon as I finish this quick lesson, just kind of going over binomial distributions using the book as a guide. So as I read through this, there's quite a bit in the way that it's presented that to me doesn't make really good intuitive sense. And so don't beat yourself up if as you read through it, it doesn't just come to you crystal clear as you might like. Binomial distributions can be a little bit confusing, and so hopefully working through this or walking through this now will help with that. So think of the term binomial. The prefix bi indicates that there's two something. So, kind of in a binary decision, it's a yes or no problem. There's two options. You're going to have success or failure. So just kind of start with that premise in mind. That by the term binomial, it's going to have something to do with two possible outcomes. And yes, there is something called multinomial. We're not going to get into that at this time. So we're just going to stick with binomial. And so we've got binomial experiments here. I've highlighted some of this and made some comments. So in binomial experiments, think about it or understand that this is a discrete probability experiment. And remember what that means, discrete versus continuous. That discrete, the outcomes can only be whole numbers or they can be counted, where continuous numbers can be, they're a range of numbers in decimal points, and there is no clear distinction as you really move from one to the next. They're just continuous, and so you just go right down the scale in very granular fashion and in decimal format. So keep in mind that it's not only a binomial, but it's in whole numbers. So it's something very easy to count in whole numbers. And you've got these four factors right here in the definition that a binomial experiment satisfies these conditions. I know in the homework and the quiz, there's some questions related to is this or is this not a binomial problem or experiment, and these are the four definitions that help you answer that. So in one of the first ones where it says the experiment has a fixed number of trials, each trial is independent of the other trials. So by being independent, that means we have replacement. So whatever we do, we're putting whatever we're testing, whatever we're studying. Once we get one outcome, we replace it, and so it's always with replacement. And in addition to that, one of the notes that I added here is that the experiment has a fixed number of trials. So this is the N. This is the N. We're going to look in a moment of the notation for binomial experiments. And this is the N. It's not based on anything other than the experiment design. I know a lot of time in statistics, you sit there scratching your head wondering, where did they get that number? Or you might think, what does that symbol mean? What does that letter mean? Well, in this case, when we're talking about the fixed number of trials, that's just whatever the experiment designer has selected. So there's no real rhyme or reason about where did that N come from. It's just something that the experiment designer chose. And so the next one we're talking about, there are only two possible outcomes. So that's the bi of the binomial. There are two possible outcomes of interest in each trial. Each outcome is typically classified as a success or a failure, and don't think of that as a positive or a negative. It just means a yes or a no. And so success is the P, failure is Q, which can also be stated as 1 minus P. So think about, you have a 100% probability of all possible outcomes. So if those possible outcomes that are success are P, 100% minus that amount is going to be the Q, which is the failure. And this is the rule of complements that we've talked about before. So we'll be using that particular rule quite a bit. The third one is the probability of a success is the same for each trial. We see this a lot in the quiz and in the questions, that the probability of success is the same for each trial. And so one of the things as I looked through this that I think was a little bit confusing, it would be a lot easier to understand if they only used classical probabilities, because in classical probabilities, remember that we're thinking about a limited sample set, like the six-sided die that we use all the time, or 52 cards in a deck that we use all the time. And so in those cases, it would make it really clear where these probabilities come from, because we understand that more intuitively. But in a lot of these problems, they're actually using empirical probabilities, which makes it seem less likely or a little bit more gray when you start thinking about the probability of success and how concrete is that probability of success, how firm is it, how literal is it. And so in a lot of these problems, even what I'm going to scroll down to in a moment, you'll see they jump back and forth between classical probabilities and empirical probabilities. So don't let that confuse you. In a binomial experiment, it can be based on either a classical or an empirical probability, and experiments must be with replacement or the probabilities change. So the third rule here is that they must be the same in each trial. So that's, again, why there's a requirement for a replacement. And then finally, the random variable x counts the number of successful trials. And this is a little bit confusing too, and we'll look at that in just a moment a little bit more. And, I would say that x is the number of successes being tested in an experiment, as maybe another way of looking at that. And perhaps we'll touch on that as we scroll down and work through this. So here are the four factors that you really need to understand, pay attention to, focus on when working a binomial experiment. So these are the four things that you really must have. And I'm really going to start in the middle here, the P and the Q. So the binomial piece of it, the bi piece of it again, is a yes or no, success or failure. And the success is denoted as P. That's the symbol that's used in indicating that, yes, this is a success. It meets the criteria that we've set out in the problem. And Q then, of course, is the probability of a failure in a single trial. So Q, again, equals 1 minus P. So P and Q are pretty straightforward. It's either success or a failure. The two other symbols that are important here are maybe a little bit confusing, maybe a little bit gray. And so again, the number of trials it's just a number that the experiment designer comes up with. There is nothing that determines what is an appropriate number of trials. This has no relationship to the number of possible outcomes or sample set or any of that. It's just simply the experiment designer says, I'm going to pull 14 cards. I'm going to pull 12 kids from a room. I'm going to hit 17 golf balls, whatever the case is. So the number of trials is just whatever the survey designer chooses it to be. And then the one that I think is the most confusing, really, so you kind of really have to focus on this, is the random variable represents a count of the number of successes in trials. And so really what this is, it's the range of potential successful outcomes. And when it's drawn up like this, it makes it potentially a little bit confusing. And so, where the little x, it's always referred to as little x, and when it looks like that, is really, what are the potential outcomes? And so this is saying you could have an x with 0 successful outcomes. You could have an x with 1 successful outcomes, 2, 3, all the way up to n. And so, of course, this n is the same as this n. So if you have 17 trials, this potential x outcome, the number of successes, could be 0 all the way up to, in that case, 17. So this n, and you'll see this frequently in statistics, this kind of denotation where you start off counting by the numbers and then you go dot, dot, dot up to n. And so you have to think, okay, what is n? Is it my sample size? What is the n? So in this case, the n is the number of trials. I can't remember what note I put here. Yeah, so it's just given in the problem. I discussed that. What note did I put here? Yeah, so again, the probability of successes, it's easier to think of if it's classical, but it may also be empirical. We discussed that. So, so they give you this card example, and again, so, think about what is the n here? Well, the n is 5, only because the experiment designer chose to pull 5 cards. No real rhyme or reason to that. I think in this particular case, they're looking for clubs, if I remember. So here we have the n is 5, S, or you might look at, so success, which we've also called P. So this could be a little p right here is selecting a club, and Q, or a failure, is selecting any other suit. So even though there's 4 potential outcomes, only one is a success, and then anything other than that is a failure. So again, that's a point that might be confusing to you when you say, well, there's 4 potential outcomes. There's 4 suits in a deck of cards. Well, if the problem had said something about the probability of choosing a club or a heart as opposed to just a club, then it's not a binomial problem anymore, because you have 3 potential outcomes. You would have club, heart, neither club nor heart. And so because it says the probability of selecting a club versus any other suit, that makes it binomial. The success is a club, a failure is any other suit. We have an n of 5 because there's 5 trials. We pull 5 cards. In this particular case, we have 2 successes. 2 clubs were drawn in these 5. And so that's not the same thing as a sample to say that this is not suggesting that 2 out of 5 cards within the whole deck are clubs. That's not what we're testing. So don't get confused there either, because this looks kind of like we're doing a sample problem, but that's not the case either. And so here this becomes a little bit confusing. So we have in this trial here, we have 2 successful outcomes. So x equals 2. Remember that the x could have been 0, could have been 1, 2, 3, or 4, or 5. Our x turned out to be 2. You could also say that our p is also 2. And so it's confusing here because they're using p and q. Now we're back to the probabilities, and so it's a little bit confusing because they're kind of interchanging or intermingling the same notation. So here they're just showing you what the probability that we know of drawing a club would be is 1 in 4, and the probability of a failure is Q. It's the reciprocal of 1 in 4, so it's 3 in 4. And so the random variable x represents the number of clubs in the 5 trials. So again here, when we look at the range of values that x could be, it's 0, 1 through 5. For instance, in our case, we have x equals 2, because in our experiment, 2 were clubs and 3 are not clubs. So the note here, what did I say? Note that there are multiple possible outcomes for suits, but for the experiments broken down into the binary of clubs versus not clubs. Covered that. And so when we really work this problem, and what we're trying to solve for is, by drawing 5 cards, what is the probability that 2 of those cards are clubs? And so again, you need these 4 pieces of information in order to be able to determine that. And so this is a different problem, but for the problem up here, or any of these problems, you need to know those 4 pieces of information. Okay, so this is a different, and so this is where I was talking about. So up here, this is a classical experiment or a classical probability problem, and now they're jumping into a problem where it's an empirical probability, because it might be confusing to you when you say a certain surgical procedure has an 85% chance of success. Well, where does that 85% come from? Up here, the probability of success being 1 out of 4, the probability of failure being 3 out of 4. It's very clear because it's a classical probability. But down here, all of a sudden they're talking about something with an empirical probability. Well, how do I know this 85% is an empirical probability? I really don't. It's just given to me in the problem. I mean, it could be a subjective probability. We talked about this in class a little bit, where a doctor might just say, hey, it's an 85% chance of success. And, it warrants the question, how do you know, doc? Is that based on your own outcomes and how many times you've done this type of procedure or surgery or whatever it is, or is it based on trials done across the country? So kind of going back to the rules of a binomial probability, given that the likelihood of outcome and the probability of outcome has to be the same in each and every trial. Is it the same from surgeon to surgeon to surgeon to surgeon, and with this different equipment and different operating rooms and everything like that? So that's why I wish the book would stick with not use. I wish the book would not use empirical probabilities in trying to explain binomial experiments, because I think it's a whole lot more crystal clear when we're working with classical probabilities such as decks of cards or rolls of dice, etc. So in any case, let's go with it because they're forcing us to. So we have to take it on assumption that this 85% applies to all procedures equally. And so the solution down here gives us the 4 numbers that we need to be able to solve the problem, or what we're going to focus on. N is the 8. So the doctor performs this procedure on 8 patients. The random variable this is the random variable here. The possible outcomes of success are anywhere from 0 to 8. So we can study any one of these. We can look at 3. We can look at 6. We can look at something like 5 or more, or 3 or less, or 2 to 4. We can calculate the probability of any of those being, or the likelihood of their occurrence. How we define the problem. But the probability of success is 0.85 or 85%. The probability of failure is 0.15, and this relates to any individual trial or outcome. So don't think of this as 85% likelihood of getting that there would be 5 successes. It's any one of these could have an 85% chance of success and a 15% chance of failure. So we're going to calculate the likelihood that 3 out of 8 were successful, or 6 out of 8 were successful, or 0 out of 8 were successful. And the n, of course, is the 8. And so that's something I think is very important to really wrap your head around and make sure that you understand what those 4 factors are that are important in a binomial probability calculation. And there was something, so we're not going to finish working that problem, but we're going to come back to some. So don't think I'm abandoning you with just that information. So this particular information that's provided in the book, I have a little bit of a problem with. I don't like the way that they've presented it. And so really what they're saying here is from a random sample. No, that's not what I wanted to see. It's kind of the same thing as the theory of large numbers, what I was getting ready to read. So really what they show here is just this they just provide this information for you. Recent survey of 1,520 adults conducted to study the way in which Americans use social media. One of the questions from the survey and the responses, yes or no, shown below. Do you ever use the internet or mobile app to use Facebook? Of these 1,520 adults, 68% said yes, they do. 32% said no, they don't. And then it says, why is this a binomial experiment? I don't think it's a binomial experiment. They're saying that it is, but I don't think that it is, because you don't have the empirical probabilities yet. This is establishing the empirical probabilities. So from this, we could do a binomial experiment, but I don't think that this, just by the way it's presented right here, in fact, is a binomial experiment. It's go back to the doctor problem above, where they say 85% of the outcomes are a success and 15% are no, or not a success. And so those numbers came from some empirical probability, some study that was done before we started doing the binomial probability problem. And so I don't like the way this is presented, calling this a binomial experiment, because to me this is just the empirical probability, or the sampling that was done to calculate an empirical probability, and setting me up to now where I can do a binomial experiment. So just a little side note, that as you're reading through these, what's in the text, and you find it confusing, don't feel like it's just you. I'll tell you, I must have watched, I don't know how many YouTube videos at different going over different probabilities and binomial probabilities, and everybody approaches it a little bit differently. In fact, I think the more you watch, I think the more confusing it might become, because people use different notation, people use different terminology. My terminology and notation might be confusing to you. I hope it's not making it worse. But in any case, I just wanted to go back and explain some of what we see in the book. And so this really is where we get down to the calculations that are involved in a binomial probability. It looks like a whole lot of mumbo jumbo. I know there's absolutely nothing intuitive about looking at that formula right there. So don't think you're missing something when you're looking at it and thinking, oh my gosh, does the rest of the class, can they look at this and it makes heads or tails of sense to them? The answer is no, it does not. But there's a couple of things that I want to point out in this. So this is the probability of any one of those x's. So above, where we had the x being anywhere from 0 to 8, or 0 to 17, or 0 to 0, 1, 2, 3, 4, 5. So this says I'm going to choose any one of those, or I'm going to choose some defined range from within those little x's. So this is what I'm studying right here, is the probability that I want to study. If I have an n of 12, I want to study. If 4 of those were, what if just 4 out of 12 were successes and 8 were failures? What is the probability of that? I might have as my x, what is the probability that 6 or greater is a success, and less than 6 is a failure? And so this is the actual math that goes into that calculation. You will never, ever, ever in this class have to do this as a calculation that I'm aware of. I hate using absolutes. The tool that's provided for you in Canvas does all of this work for you, and we're going to visit that in the second video that I'm going to do in just a moment. But one thing that I do want to point out here is, see this part of the formula that I just highlighted? When you see this notation, this can really be confusing, and I'll tell you why. Because this little p to the x, that's a mathematical formula. So that's p to the x, and it might be whatever the x is. If I have 3 here, so it's p to the third power. If I have 6 here that I'm trying to decide, it's the probability excess to the 7th power. Whatever I have here as the x is the power that I'm raising p to. Same thing here with q, where I'm raising q, how we define the probability of failure, to the n minus x level. So that's the number of failures. So the point I'm really trying to make is, this is math. When you see this notation raised to the powers, this is math. This is not math. This little n and this x right here, this is communicating to you really what it is that you're studying. This is not math. All of this over here, right? Let me see if I can highlight this without. So all of that I just highlighted is what's behind this. So that's the actual math. All this, see this p to the z times q to the n minus z? That's the same as what you have right here, p to the z times q to the n minus z. All this looks new, but it's the math behind this. So all this is telling you, this is like a communication of what the problem is looking for. And so this is just how many trials are in the problem. The x is what's the probability I'm looking for. This is just a variable that we're going to calculate in a moment, but this is the actual calculation here. So in any case, what I'm trying to point out to you is when you see this notation, which is basically a variable in the middle, a small letter to the left and a small letter to the right in subscript, that's not math. And so when you look at this and try to figure it out and say, golly, I don't know what I'm supposed to be doing there, don't worry about it, because you're not supposed to be doing anything there. Somewhere else there's a formula that's providing you the math that you're supposed to be doing. We haven't talked about factorials in class. I don't know if you have seen or recall really what a factorial is, but whenever you see this notation, the n could be a number. This could be factorial of 8. It could be the factorial of 3. It could be the factorial of 746. It could be the factorial of anything. So whatever n is, so n is just a variable. And so this is saying that variable, take the factorial of that variable. And remember what a factorial is. So a factorial is the number, in this case, that the variable represents, times every whole number all the way down to 1. So the factorial of 5 is 5 times 4 times 3 times 2 times 1. Factorial for 7 is 7 times 6 times 5 times 4 times 3 times 2 times 1. You get it, okay? So I'm certainly not going to do a bigger number than that. So wherever you see this exclamation point, that is a math notation for factorial, and where you do, again, if it was the factorial of 3, it would just be 3 times 2 times 1. That's what that exclamation point means. Here it looks a little bit funny. This exclamation point goes along with the n minus x. So you do the n minus x, get whatever that outcome is, and do its factorial times x factorial. And again, you're not going to have to do all of this math. I just want you to, I'm trying to demystify it a little bit when you're looking at this. What the heck am I looking at? And every single one of these variables, every single one of them, it's only 4. You know, it's these same 4 that are up here. It's these 4 variables. So, you know, don't look at it and say, oh my gosh, where are they getting all those numbers? It's these 4 variables. N, P, Q, and X. Probability of success, probability of failure, number of trials, and whichever random variable we've chosen to study from the range of potential random variables. So it's only those 4 numbers. Don't look at it and you know get overwhelmed because it's some crazy looking formula. And so again, just trying to trying to bring it down a little bit to reduce whatever anxiety it might represent when you look at that and say, I have no clue what that means. And you may still have no clue what that means, and that's okay, because you don't have to calculate it yourself. We showed some tree diagrams the other night, and this is kind of the laborious way. This is kind of the hand crank way, if you will, of solving these problems. I don't even really like to do it this way, so I'm just going to move on past it. You'll never have to do one, I don't believe, that way. And if we need to go over it in class some more, we will. I showed it in class just because I wanted you to kind of have an understanding of what it is, but let's move past it for right now. And so this is just an example of somebody working through one of these problems. And again, you can see that the 4 variables are the same that we have up above. Probability of success, probability of failure. N is the number of trials, and in this case we're studying the probability and outcome of 2 out of those 3 trials. And so this is the actual math. You can see the 3 factorial, 3 minus 2 factorial, 2 factorial, and look what happens here. This is easy. 3 factorial is 2 times 2 times 1, so that's 6. 3 minus 2 is 1. 1 factorial is 1 times 1 is 1. 2 factorial is 2 times 1 is 2. So 6 over 1 times 2 is the same as 3 over 1. So you get 3. So, again, it looks complicated. It looks, big and heady and crazy and all that stuff. And if you just go through it methodically, you're like, wow, it's really not that much. It's just a lot of math all kind of tied together, but the math itself is actually fairly straightforward and simple. And so I think that's pretty much all I want to go through binomial probability distributions right now. I'm going to work some actual problems in the next video. Let's see what my note was here. Construct a I guess one final note, and this is actually kind of important. I'm sorry. Construct a binomial probability distribution. That term right there is important. When you see that, construct a binomial probability distribution for the number of adults who say yes. And this problem is talking about, maybe it's yes, do you use Facebook? Maybe it's yes, do you use LinkedIn? Remember, it can't be do you use Facebook or LinkedIn? Do you use Facebook or Twitter or something like that? Because if it's an or, now you've got more than one potential outcome. But if it's do you use Facebook, even though there's 5 different variables here, it's Facebook versus everybody else. So everybody else is on the failure side, Facebook's on the success side, or however the problem is defined. But this thing right here, a binomial probability distribution, is actually all of the x's are included. So remember where we said the values of x, if I have an n of 6, then the values of x are 0 through 6, so I can study 0 successes, 1 success, 2 success, 3 success, etc., etc. So here, what you're looking at, and again, it looks like it's very busy, it's a whole lot of numbers, it looks confusing, a little bit overwhelming. It's really not. The probability of 0 successes, this is that same formula we have up above. And so this, it's cleaner to write this 6C0 as opposed to that crazy, drawn out version of the formula. So it's just a cleaner notation way of doing it. Then you have the probability of successes, probability of failures, and then they just kind of work through that. So if you look at this, you might be confused. Where do they get this 1? Where do they get this 6? Where do they get this 15 and this 20 and this 15 and this 6? Well, remember, up above, they show you how to do the math that's behind this notation. So if you were to take this information, n of 6, in this case, like a p of 0, p of 1, p of 2, whichever one you might choose. I'll just use 3 as an example. So if I have an n of 6, a p of 3, so I'm figuring out what is the probability of 3 successes out of these 6 trials, and I've got, the probability of success is 68%, probability of failure is 32%. So how do I get the 20? Where does that come from? Well, if I go back up here, and if I was to plug the numbers in here, I think we have n of 6. So 6 factorial divided by 6 minus 3 is 3 factorial times 3 factorial. If you do all of that, I guarantee you what you're going to get is 20. That's where that 20 comes from. So they just don't have that more complicated looking formula. They use this notation instead. But when you just look at this table, you're looking at it going, I have no idea where the 1, 6, 15, 20, 15, 6 come from, and that's where it comes from. And again, what this is, it's the binomial probability distribution. So you're calculating the outcomes for everything that 6 can possibly be. 0, 1, 2, 3, 4, 5, 6. So see, here's the 0, 1, 2, 3, 4, 5, 6. We're calculating all of those here. Now, before I say again, I'm done, let me look down. Yeah, I think I'm pretty much done. Okay, signing off. Look for the next video.